Hello, my name is Gavi Yanis, and I'll be presenting the first part of our project. We are Group 7, and our application is called RentWise South Florida. RentWise is a machine learning tool designed to help renters understand whether a listing is underpriced, fairly priced, or overpriced, based on real market data. I'll start by walking through the problem we focused on, the solution our team developed, and how it compares to existing tools. After my section, the rest of the team will go into the system design, live demo, and testing. South Florida has become the least affordable rental market in the country, and Miami is ranked number 1 for unaffordable rents. The median rent here is now higher than what an average household can reasonably afford, and more than 30% of renters are spending over a third of their income just on housing. Despite these challenges, renters still lack a simple way to understand whether a listing is actually priced fairly. Tools like Zillow or Rentometer show numbers, but they don't explain whether a price is reasonable for the area, which leaves a big transparency gap. Here's how our solution works and how it helps renters make more informed decisions. The user starts by entering the property details, things like the zip code, number of bedrooms and bathrooms, square footage, property type, and amenities. Our machine learning model then predicts what a fair rent should be for that property. We compare that predicted value to the actual listing price, and based on that difference, the system classifies the listing as underpriced, fair, or overpriced. Our primary users are renters who want quick, clear guidance without needing technical knowledge, but the tool can also support landlords checking their pricing, housing researchers, and policymakers who track affordability trends. Most existing tools either give a basic rent estimate or rely on national models that don't reflect South Florida's markets. They also don't tell renters whether a specific listing is actually fair. RentWise is different because it provides a fairness label, uses a model trained specifically on South Florida data, and is designed with renters as the main audience. It's also a live, free web application that considers multiple property features, which makes the insights more personalized and more useful for real-world decisions.
Now that we've gone over the scope of our project, I will now go into more detail on the system architecture and how we built our project. So for the front end, we decided to use a modern and fast web development stack. This included using React, TypeScript, and Vite. Our front end is composed of 5 different key components, which includes the property form, which handles all of the user input, the prediction result, which displays the model's output, feature selector, which uses toggle amenity flags, saved listings, which gives users the ability to bookmark listings that they want to revisit in the future, and the research dashboard, which displays aggregate price trends for the South Florida market listings. The backend API is built with Fast API, Python, and Pydantic. In this implementation, we decided to go with all Python based in order to eliminate any boundaries between the API and the machine learning pipeline. Our API exposes 2 different endpoints, a post/predict endpoint that receives listing details and returns a rent prediction, and a get/trends endpoint that returns aggregate market statistics for the research dashboard. All inputs are then validated through Pydantic before they ever reach the model, and this ensures that the system handles bad or incomplete data. The backend is structured around 4 different object-oriented classes: rental property, prediction request, pricing assessment, and rent prediction model, all which keep the code organized and maintainable. Additionally, this in the API includes a zip to city mapping logic, since the users input a code on the front end, but the model expects a city name. This is all done so that the translation happens automatically in the backend. Finally, the machine learning pipeline, which in this case was the part of the project that was mostly my responsibility. We trained the model on over 2,800 South Florida rental listings, which were sourced from 2 Kaggle datasets. These datasets covered multiple cities, property types, and listing sources across the region. I then applied feature engineering on those datasets to extract additional signals from the raw data. This included bed-to-bath ratio, an amenity score that sums all of the binary amenity flags, and a numeric zip code for capturing the local price patterns. The model is a gradient boosting and random forest ensemble. Each of these I will go into more detail in the following slides. We've predicted log price rather than raw price in order to reduce any skew within the dataset. We saw that rental prices have a small number of high outliers and can distort a model trained on raw dollar values. And taking the log of this compresses the range and makes prediction much more stable. Finally, once a prediction is made, the system classifies the listing as using a plus or minus 10% log unit threshold to determine whether it is underpriced, fairly priced, or overpriced. Next, I will go over all of the key design decisions that were made during this project. So for the first key design decision, we have deciding on the machine learning model type. So eventually we chose an ensemble of gradient boosting and random forest over deep learning and linear regression. I will go over in more detail on what gradient boosting and random forest is in later slides. So the reason why we made this decision is because deep learning was ruled out since our data set was pretty small. It had roughly 2,800 rows, which generally is too small for deep learning to generalize data well. On the contrary, linear regression was too simple to capture the nonlinear relationships between features like location, size, and amenities. In the end, the ensemble approach gave us the best balance of both accuracy and stability, and then as an added benefit, it produces feature important scores that let us explain predictions to non-technical users, which is something that deep learning cannot easily provide. For the second decision, the design decision included technology stack. So as mentioned before, we decided to choose FastAPI, React, and Scikit Learning over frameworks such as Django and vanilla JavaScript. The all Python backend eliminates any integration barrier between the API and the machine learning pipeline, as mentioned before. And FastAPI's native Pydantic validation handles input validation automatically. And additionally, React's component model is well suited to our multi-step stateful form. For the third design decision, we have the pricing threshold. So we chose a percentage-based threshold of plus or minus 10% rather than a fixed value dollar amount, because South Florida spans a wide range of markets. This includes from rentals being $1,200 in Homestead to some properties being valued at $4,000 in Miami or Brickell. So a flat dollar threshold would be too strict for affordable units and too lenient for luxury ones, while a percentage-based approach scales proportionally and stays consistent across the entire market. The 10% value is also calibrated to our model's actual average prediction error, so it reflects a real precision rather than just an arbitrary cutoff. Finally, we have the dataset strategy decision. So we, in the end, evaluated 5 data sorts. And for the final important decision was on dataset strategy. So initially, we had evaluated 5 dataset sources that would contain different listings. And in the end, we rejected 3 of them due to them not having sufficient rental content or having listings that were outside of South Florida. The 2 accepted Kaggle datasets included the USA housing listings and the apartment data datasets. These provided individually over 1,400 South Florida rental rows after some filtering and some alterations. We also ruled out live scraping due to legal and ethical concerns around terms of service, as well as the additional engineering complexity that it would have added. Next, I will be going into a little bit more depth on the machine learning model that was used during our project. The machine learning model was built and trained using the Scikit library. So the model accepts 3 different categories of input, which include numeric features like bedroom, bathrooms, square footage, and coordinates. Binary amenity features, which either are 0 or 1, including flags like pool, gym, and washer and dryer. And lastly, categorical fields that take in string encoded types. This includes property type, city, and parking type. So the 2 different algorithms that were used for training our model included gradient boosting and random forest. Gradient boosting is a sequential learning algorithm that starts by making a rough initial prediction and then builds a series of decision trees where each new tree focuses specifically on correcting the errors that the previous tree made. After over 100 iterations, the model then progressively gets more accurate by honing in on the cases that it kept getting wrong. This makes it particularly strong in our structured tabular data, where patterns between features are complex and nonlinear. Next, we have random forest, which works a little bit differently, as rather than building trees sequentially, it builds trees of independent decision trees all in parallel. Each is trained on a random subset of the data and features. It then averages all of the predictions together, And because each tree sees a slightly different view of the data, the averaging process cancels out individual errors and produces a more stable, reliable result. And this is what makes it effective at reducing any overfitting of the data. Together, these two algorithms complement each other well, as gradient boosting contributes raw predictive accuracy by iteratively correcting any mistakes, while random forest contributes stability by averaging out any variance. In this case, we carried out gradient boosting to be 60% of the weight, as it was the stronger performer on our data, and then random forest carried out 40%. And then their outputs are combined through soft voting to produce the final predicted log price, which is then converted back to a dollar figure. Finally, the prediction is then run through a pricing classification logic in which the difference between the listed price and predicted price is calculated. And if it exceeds 10% in either direction, then the listing is flagged as either overpriced or fairly priced if it is in between that 10% threshold.
Hi, my name is Vanessa Lamarck, one of the front-end developers for Rentwise South Florida. I'll be walking you through the live demo of our application using two real scenarios in Miami Beach. The first listing will be a 2-bedroom, 2-bath apartment, 900 square feet, asking price $23.50 a month. The amenities include a pool, gym, balcony, and in-unit washer and dryer. Before I fill this in correctly, I want you to notice what happens if I try to submit with missing or invalid data. As you can see, the form won't let you proceed. That validation is happening client-side before the request even reaches the backend. Now, let's fill in all the correct fields and submit. Upon submitting, the model is running the prediction in real time. As you can see, it predicts a fair market rent at about $24.43 for this unit. The asking price is $23.50, which is about 3.8% below the predicted value. Rentwise labels it fair price. This listing checks out, and the renter can feel confident moving forward. We're going to save this listing and check it against another property that we find interesting. Now let's look at a second listing. Same neighborhood, same zip code. This one now is 1,100 square feet. The asking price is $3,400 a month, and we're going to add one extra amenity, a gated community. Now after hitting submit, we see that the model predicts fair rent at about $26.69 a month. The asking price is roughly about 28% above market. Rentwise flags this as overpriced. So same neighborhood, same bedroom count, but this listing is approximately 700 above what the market supports. Without Rentwise, a renter has no way to know this. That's exactly the gap we built this to close. Now let's save this listing and navigate to our Save Listings feature. As you can see here, we have both listings now saved. This is where the apartment hunting actually happens, comparing multiple options at once. Each saved result shows a fairness verdict so you can make an informed decision side by side. Now, if you wish to remove a listing, you can do so with the remove button at the bottom. Now let's navigate to the last feature, the research dashboard. This dashboard shows aggregate trends across the dataset, average rent by zip code, property type, bedroom count, and the price impact of individual amenities. This is designed for housing advocates and researchers who want to understand South Florida's rental market at a broader level. As you see here, there are various charts and tables to show this data. That's Rentwise. Now to Ibrahim.
Hey guys, so I'm going to be covering the product features, the testing validation, and whether or not our project actually solves a problem. So to begin, For our product features, the first main thing is the property input form. That's where the user puts in things like the zip code, the listing price, bedroom, bathroom, square footage, and any other type of miscellaneous information that could affect the price of rent for housing. Once they submit that information, our machine learning model gives back a predicted fair rent and tells them if the listing is underpriced, fair, or overpriced. We also added a saved listings feature so you can save any listings that you put into the application itself, and users can bookmark what they want to save for later if they think it's a good price or overpriced or whatever reasons they might have. And lastly, there's a research dashboard which shows trends like rent by zip code, property type, bedroom count, things like that. For testing and validation, we basically wanted to make sure everything was working correctly from the data side all the way to the final prediction. So we began with testing both our data sets to see if they loaded properly, cleaned properly, and merged without errors. We also checked for any missing values and made sure things like price and bedroom values looked valid. On the backend side, we made sure the API accepts correct inputs and clear error messages when something is missing or invalid for any debugging that we might have to do in the future. And then for the model itself, we used a voting regressor with gradient boosting and random forest, and we evaluated it with 5-fold cross-validation to make sure the results were solid and consistent overall. Now, to the question, does it solve the problem? Overall, I would say that the project does solve the main problem that we started with. The whole issue was that renters usually can't tell if a listing is actually fairly priced, and our app gives them a direct answer by labeling it as underpriced, fair, or overpriced. Also, instead of just showing listing prices or market averages like other platforms, our model actually predicts what the rent should be. And we made the app renter focused, so it's simple to use and easy to understand. Plus, since the model is trained specifically on South Florida data, it's more relevant to South Florida. And yeah, that's my part.
Here's an overview of all of the team's contributions during the project. Gabby was our project lead and front-end developer. She helped us with overall project coordination and sprint tracking, as well as development of the front-end component architecture and navigation. And finally, she was the lead in maintaining the academic documentation. Vanessa was our other front-end developer. She helped with UI design and implementation, cleaning, merging, and enrichment of the data pipeline, and lastly, dataset validation and geocoding. Ibrahim was our backend developer. He helped with development of the Fast API server and design of the endpoint. He also helped with machine learning model integration and core setup. And lastly, input validation of the API endpoint and error handling. Lastly, I was the machine learning engineer. I helped with the model training, tuning, and evaluation, feature engineering and selection, and report generation of the evaluation of the machine learning model. And to conclude, these are the conclusions that were drawn from our project. So originally, South Florida renters lacked objective pricing tools, and with our project, RentWise helps fill that gap with data-driven fairness and classification. Our machine learning model used a combination of gradient boosting and random forest ensemble to predict fair rent using local data, amenities, size, and location. Our full stack application is live, tested, and ready for real-world use. And lastly, all of our pre-processing tests have passed, and the model produces region-specific predictions with explainable thresholds. And that is the conclusion of our presentation. Thank you very much.